All right, now I'm going to pass it over to Dr. Nazzal, who's going to kick us off on some insights from our field testing case studies.
So thank you. Thank you. Thank you, Sam. Um, so our case studies basically focused on the studying. We have two case studies, and basically the one that I will be presenting today is focusing on the infrastructure elements. We wanted to answer one main question, which is how the different infrastructure elements basically affect the safe operation of autonomous vehicles. We had two main questions. There was a lot of focus, as you have seen, on pavement marking. And as a result, basically our first and main focus was to see how the pavement marking is affecting the a safe operation. And also we wanted to see what are the properties and characteristics of the pavement marking that are needed to ensure safe operation of the AVs. The other important thing is that we wanted to see how different road surface distresses and properties can affect the AV operation. And here we focused on, I would say, two main things. The first is the pothole, which is very common distress in pavements. And then the other important thing is the crack sealant, which is a treatment to a very common distress, which is cracking. So we're trying to see if there is any impact and or how that the potholes and the crack sealant affect the safe operation of AVs. So to do this, we used actually different vehicles, but the focus here is really on a level 3 testing that we have done. And basically the test vehicle was a Tesla Model 3. We have operated it in a full self-driving. Basically, I'm showing the two versions used. Just to let you know, this experiment and the case study took place during the summer of 2024 all the way till basically winter of 2025. It was completed, I would say, by March of 2025. And the main reason why we have done that is that we wanted to make sure that our study covered basically summer, fall, as well as winter. And what we have there is basically we added and mounted a sensor system that was basically developed and designed for specifically for this study. And that system have several sensors to help us understand the different infrastructure elements and their properties. So we have a ouster LiDAR. We have two cameras, and basically one that you see here in your left, which was mounted on top, and that's focusing really on the road and road elements, including the pavement marking. And then we have another camera and the first camera, I would say that it had a high resolution images. The second camera was really only focusing on what the screen of your Tesla. And then we had a GPS IMU. All of those sensors basically enabled us to have a look at basically when there is a disengagement or there is a, I would say, a false detection, which we will be talking about it in a moment, or a non-detection. Then basically whenever we're having an issue or the vehicle is having an issue, we're documenting it and everything is being synchronized with the other data. So we did some, I would say, sensor fusion, which enabled us really to determine whenever we have a disengagement or a false or a detection or a non-detection. Basically, we will be able to see the properties of the infrastructure elements, the different infrastructure elements at that point. So the sensors, and just to give you an idea, if you can go to the next, please. This is basically the data that we have. Again, the frequency was 10 hertz for the LiDAR, the camera, both cameras, and the GPS, because we wanted to have a better location or an exact location. We had a 50 hertz. The LiDAR provided, of course, the point cloud, which included different things, but I think one of the most important things that we were looking into is the intensity. And then basically, as I said, there was one camera with a high resolution, and then basically we had another camera that was a lower resolution and focusing on basically the screen, the Tesla screen. One important thing, that all those sensors were operated using a ROS operation system, so that enabled us basically to synchronize everything, all those sensors together. Yeah, if you can go next slide. So we did several routes. One important thing is that we did actually 10 routes, but then we ended up with selecting certain routes where we did most of our runs or all of our runs on those. Why we selected them? Basically, we wanted a route that represents a two-lane roadway, multi-lane roadway with different pavement marking. A poor, good, and no pavement marking were considered. We considered also a urban setting as well as a rural setting. We considered also places with good pavement condition and poor. And when I say good or poor, in terms of having these stresses and focusing on whether we have a crack sealant or places with extensive crack sealant and other places without. This is basically an overview of the routes and basically the location that we have done those. One important thing is that we have driven those routes at different time of the day and different, I would say, dates, and we were focusing on the location of the sun with respect to the driver as well as the camera. We were also focusing on different weather, including wet, dry, as well as snowy days. We were focusing also on cloudy days as well as sunny days. And as I said, we were focusing on a different time of the year as well as a different time basically of the day, mainly focusing mainly that was important so that we can capture how the effect of the sun location will impact the driving. For every case, we did several runs. You can go to the next slide. So with all those, we focused on really three types of failures. The first is disengagement, and again, I will show a video for that. A false detection, which means that if you can go back, or yeah, that's fine. That's fine. We can go start with the first one. The disengagement. This is, as you can see, as we're driving, the disengagement is defined when basically the vehicle tells us that we need to take a control. So this is basically a point of disengagement. At that time, we were able to locate just before and just after basically that incident, what exactly the properties of the different infrastructure elements, and focusing here on the pavement marking quality. The next is basically another failure mode, if you can go to the next, please, is the false detection. And here, what I mean by false detection is that we have a solid center line, and it is being detected, as you can see here in the screen, the Tesla screen, as a skipped, which can be very dangerous. And basically that means that it might basically allow the vehicle to pass. The last type of failure that we noticed was the non-detection. So, and again, that's the focus was on the center line because that might be a basically a cause of an accident. And this is basically where you can see that the pavement marking is so faded, and that the car see it at some times, but it does not see it most of the time. So basically we were able to determine that and do our analysis. So what we have done, if you can go to the next slide, is our approach is really looking at the entire data and focusing at those locations where we had the failure as we have defined. And basically what we have looked into is looking at characterizing basically the pavement marking and getting the properties that properties that can be used really to differentiate a pavement marking that might cause a failure to that might not. And basically we looked at the data. The first step was that we developed a model for detecting the pavement marking based on the images. And based on that, we did some analysis, color analysis specifically for the pavement marking. And again, we looked at places where there was a failure to places where there is no failure. And basically then we conducted a comprehensive statistical analysis to determine basically the threshold. We used 3 parameters. And if you can go to the next slide. Those 3 parameters is the Michelson contrast. It is basically based on a luminance or brightness contrast. Then we have another one, which is and again, this is how it was determined. We have also the CIE lab color distance. Again, this is more about the color difference, more than the brightness. And then the last is a RMS texture fragmentation. And basically, this is really detecting areas that might be you might have faded or no paint. And basically, this is about basically places where you are missing some of the paint there. So if you can go to the next slide. So what we have done through the comprehensive statistical analysis that we have done is we looked at basically for the different cases of this engagement, we looked at what are the properties of the center line marking as well as the edge line marking, and tried basically for the places where we have this engagement to see how those properties were different as compared basically to places where we did not have any disengagement. And again, this is based on multiple runs and multiple failures in that same area. And I would like to note one important thing is that those properties, if are based on the time of the day. So for sometimes we might have a disengagement, for example, during the morning, but then later in the afternoon or later in the morning, we might not have that disengagement. So basically, because of our analysis, we were looking at how those properties are changing and linking it to the exact place where we have disengagement at that time of disengagement. And again, our system basically enabled us to capture that. And again, everything is synchronized. And with that, we were able to obtain basically for those sections at that time, what are the failure. And what we have noticed is that statistically, the properties where whenever we have a disengagement as compared to when we do not have this engagement, as you can see, this we can have different basically thresholds for this for different properties. Mainly here we were seeing that the color distance and Michelson contrast have basically were statistically significant, and basically we were able to get that optimal threshold of the delta E of 11, and here if it is 0.06, and again this is for a yellow pavement marking center line. If it is an edge line, we also notice that with those disengagement, basically, we had the threshold was 6.6 and about 0.06 with the Michelin contrast. And again, this is for the edge line. So those are thresholds that can enable the IOOs basically to make sure that their pavement marking, if they have a higher values, then basically this will indicate that they might not be susceptible or under the risk of having the AV disengagement. We go to the next slide. So this is for the false detection. And again, this is focusing on center line marking. And this is for yellow center line marking, of course. Again, this is for 2-lane. In this case, we had the color distance, the delta E to be 9.8. Again, the Michelson contrast, it's to be 0.06, and then basically the RMS to be 0.14. Very important thing that all of those values, as you can see, are statistically significant at 95% confidence level. If you can go to the next. So the next is the non-detection. And what I mean by non-detection, basically, it is not detecting a yellow center line marking here. And basically, again, we have a color distance of around 10.6, and again, Michelson contrast of 0.03, and then basically an RMS texture of 0.22. And again, those are the values, basically, that the threshold that in our next slide that we'll be talking about it, if you can go back just 1 second, we will see that those were all those cases were gathered to basically to make a final recommendation for the infrastructure owner operators to what are the threshold for the pavement marking to ensure that we do not have any failure in terms of non-detection as well as false detection, or more importantly, any disengagement of the AV. Now, one important thing is that we looked into, and you can go to the next slide, was the LiDAR. LiDAR, we have another study that basically we have conducted, and the LiDAR is basically a intensity specifically can be used to evaluate the retroreflectivity. Currently, most infrastructure owner operator are focusing on retroreflectivity. This is the FHWA requirement, which is basically for night vision. And again, this is for human driving during to ensure that human driver will be able to see the pavement marking during the night. So basically, this is for the night vision or night visibility of your pavement marking. So the retroreflectivity is, again, without going into detail, but we have developed a model in here to capture basically based on the intensity to be able to locate where the pavement marking is, and then basically to correlate it to the retroreflectivity. Again, here we focused on the intensity because we have found that we have an excellent correlation with retroreflectivity. So what we wanted to do is looking at for the locations where we have a failure, whether it is a disengagement, a no detection, or basically a false detection, if we see differences in terms of the intensity when disengagement or a failure happened compared to basically a non-failure case. If you can go to the next slide. So what we have found is that, as you can see, that at 95%, there was really no difference. The more important thing is that in some cases we're seeing, as you can see from the p-value, which is, if you subtract 1 from that, this can tell you the probability. It is almost that there was really no difference between the intensity values where we had of the pavement marking, where we had a disengagement to no disengagement or no failure. And this is basically indicating that the LiDAR alone might not be a good, or basically retroreflectivity alone might not really be a good measurement to evaluate basically the pavement marking contrast and to ensure in case basically to ensure that we have a safe driving and operation of AVs. So basically this is one of the things that we have. Now, if you go to the next slide, please. So in here, what we looked into is the crack sealant. And as I said, we had a lot of cases where we had crack sealant, transverse, longitudinal. And basically what we noticed is, at least for all the cases that we have, there was not any confusion or any cases where the crack sealant had caused any problem in terms of the level 3 operation of the vehicle that we were using. And basically, this, I think still the recommendation is to make sure that we have a good contrast between the crack sealant and the pavement marking, and making sure that the basically color of the crack sealant is it's might be normal and do not like unusual basically crack sealant might be a cause of disengagement there. Now, the other important thing, if you can go to the next slide, please, was the potholes. Through driving, we noticed that basically the vehicle, the test vehicle at the level 3 full self-driving mode, it did not slow down at any potholes. So we did several tests with roads that have potholes. We looked at potholes that are classified basically based on the FHWA to be severe. And basically we had ones that were over 3 inches, basically, which is considered to be severe potholes in terms of depth. Again, different sizes. And basically, two things is that the vehicle did not avoid, but the more importantly is that it did not change the speed or slow down. And again, that might have a risk on the vehicle itself, but also currently or in the future, we still have that mixed basically traffic with automated and human driving, and basically that might also be cause risky driving, which again might cause accident in the future. So therefore, this is one of the things why we have recommended that there need to be a better I would say a pothole maintenance management, a plan and program for the different IOOs. And one of the things is there need to be an active basically program for detecting the potholes. Currently, it's more reactive, meaning that people are reporting the potholes rather than the IOOs detecting that. And again, the problem, as everyone knows, is that the potholes can occur quickly, and again it might be very difficult for IOOs at the current time to manually detect the potholes and repair them, again specifically during the winter. Now if we go to the next slide, there were another issue that we have noticed, which is at the rear road crossing. Basically in all cases the test vehicle at full self-driving mode did not really slow down, while at the same crossroad which had been deteriorated, basically we had a human driver would have went to a speed of less than 20 miles per hour, but the vehicle basically continued at normal speed, and basically that might also be a cause of basically danger. So this is an indication that there might be I think two solutions there. One is making sure that all those railroad crossing are in a good shape, which is might be hard, or there need to be a notification by the OOs basically to the AVs about the condition of those railroad crossing, and basically through I2V communication. So with that, I think that we have the recommendation, and this is the next slide. We have the following recommendation, and again, this is the first is for the pavement marking quality thresholds. Basically, for yellow center line, we are recommending basically a delta E of 11 or greater. The Michelin contrast at least 0.06, and then RMS texture should be below 0.14. Then the other important thing is the white edge line. We need it to be at least 6.6. And for the Michelin contrast, it should be at least 0.06, and the RMS should be below 0.22. We are seeing that using retroreflectivity alone for evaluating the pavement marking might not be basically good enough to ensure safe driving of AVs at a basically different levels. And this, I think, also might be applied to a level 2. Again, all of what I have presented is level 3, but level 2 will have the same thing. If you go to the next slide. In terms of potholes and a crack sealant, as I said, the crack sealant, we do not have, we did not really see an effect on the AV safe operation, but for the potholes, we're seeing that it seems it's not slowing down and it is not detecting it, and basically, therefore, there should be a good roadway maintenance program by IOOs to ensure that we do not have basically at least large potholes that might cause risk again to AVs and basically to human driving vehicles. The other thing is also there should be for railroad crossing a notification because we have noticed that basically for deteriorated railroad crossing, basically there were issues of the full test vehicle at full self-driving basically mode. There was a failure there, and basically there should be a notification to the AV of the basically how good or bad is the railroad crossing, and basically the condition for that railroad crossing. With that, I will turn it into Muhammad, and thank you.
I feel like we have a couple great questions that we're going to want to let people know. We are at the time block, but if we can take just a moment to go through the ones that were answered previously. If you have any additional questions, please put them in the Q&A box, and we'll look forward to doing that. And again, what was presented on will be recorded, and so that you can share with everybody. So real quickly, if you could just address, Samantha, how agencies might measure or monitor infrastructure condition to optimize performance, and the recommendations that that was asked about, and what your reply was.
Yeah, so in that TRB web resource, we are currently working on developing an implementation strategies section, which will be in another tab. And essentially, that's more so like deployment strategies for IOOs. And so one of the sections that will be in there is essentially on conducting infrastructure readiness assessments. So I know that there are a lot of different vendors in this space which will recognize in that document, but one that just comes to mind, like I highlighted in the chat, is ESI AI. So they're an online app platform that can allow IOOs to monitor and assess their infrastructure themselves.
Thank you. Yeah, and that's the mention of ESI. Just remind everybody is FYI only, not a recommendation by the project or by anybody else, but that's great. Thank you for that. And then Dr. Nazzal answered a question that was in there about were any other vehicles used other than Tesla or the Tesla FSD for rail crossings? And Dr. Nazzal, if you want to make sure everybody, people haven't seen that answer, if you could go ahead.
Yeah, so for the NCHRP, we were looking really at the most commonly used production level vehicle with a full self-driving basically capability. And at the current time, it was Tesla. This doesn't mean that we have others, but the one that is currently most used, I would say, is basically the Tesla. And one important thing that I would say that those recommendation as will be might are important really for the level 2 and level 3, and we are aware, as Dr. Ahmed have mentioned, that there are new versions of the full self-driving even for the Tesla, but those might not be applicable for basically older version of those AVs. So our focus is really for current and maybe near future. Again, things might change, and that might really why I think there will be a recommendation that all those like whatever we have in this study might need to be re-evaluated maybe in 5 years. But again, the thing is, we wanted what is currently common practice, and that's what will be applicable really in the currently and in the near future. So yeah.
And that serves as a good reminder for the links in the chat box for assisting, for whether you're a Tesla owner or want to contribute and give response back. And I thought that the four of you did a great job describing how you actually capture a rapidly changing environment like that. So just for those who maybe didn't see the beginning of the webinar, make sure to go back and look at some of the research frameworks and approach on how not only the environment has changed rapidly on a month-to-month basis through the last year, but the approach for the research project to capture it.